Okay, so I'll begin with this setup of the problems. In my setup, I will have the following parameters, which are integers. And I will be concerned with rational approximations to n functions of d real variables. Without loss of generality, I will assume that the first of these functions are just variables themselves, and the rest is given by some map which, without loss of generality, I will assume to be defined on the units cube. And I will assume that this is C1. Well, I'll have some more constraints on this map later on. I also have one more parameter, tau, which I will assume throughout is at least 1 over n. So this will represent the exponent of rational approximations. Finally, I will define this set Sn of tau f, which will consist of all points x1, xd in the unit cube, such that and now I'll just write down several inequalities. So x bar is just this point, x1, xd. And I will assume that this system of inequalities holds for infinitely many. IM will stand for infinitely many integer vectors PQ. So that's P1, Pn, Q in Z and cross N. So I'll assume that Q is strictly positive. So that defines basically an n-tuple x1, xd, f1, fm of in an n-dimensional space, which we can approximate by rational points with the same denominator q with this exponent of approximation. Okay, so the problem, let's say problem 1 that I'll be discussing here today is under what conditions on tau and f do I have the following equation. Okay, so let me explain. So this dim just stands for Hausdorff dimension. I've got this condition tau bigger than or equal to 1 or n here. Clearly, if it equals to that parameter, my set contains all the points of the unit cube by Dirichlet theorem. So I'm really interested what happens to the set when tau is strictly greater than n. Let me just give it a label. It's D for dimension. So why I'm asking this, so I just recall the classical result, theorem of Yannick and Beresnevich. From around 90 years back, who proved that if m is 0, so basically when I don't have these inequalities, when I just approximate the real independent variables, this equation is true for any tau. Okay, there are of course more general results which in which you can plug here just a function, maybe monotonically decreasing function of Q, and can ask the same question about the dimension or more generally Hausdorff measure. But for this to work, I'll make it easier and just restrict myself to this specific form of approximation. Okay, so the other problem, which is related to problem 1, is about the distribution of rational points near the curve parameterized by this function. So if I, or more generally manifold, so if I draw a picture in 2 dimensions, pick a point on this curve, x f of x, so these inequalities basically tell me that my rational point p over q lies at distance up to some constant. Is it visible? No, not too small. Up to some constant, well, depending what do you mean by distance, Euclidean or some other, q to the minus tau minus 1. Right, so if I want to prove anything sensible, it makes sense to group together rational points with roughly the same q in size, comparable q in size, and look at the corresponding neighborhood of the manifold curve in this picture, and see what I get when I draw here all the rational points that satisfy this condition. It's pretty straightforward that if I have a good upper bound on the simply just on the count of these points, let me give a name to them. Let me just call it R of tau, and I'll introduce a parameter capital Q, which will control the size of the denominator of these rational points. So that's going to be the set of rational points P dashed over Q, by which I mean I'm just taking the first d coordinates, such that fj of p dashed over q minus p d plus j over q less than q to the minus tau minus 1, and I've got a condition on the q. Right, so basically I'm I'm asking for the little q, the denominator of my rational point, to be of no more than capital Q, no less than some constant, which I implicitly place here with the Vinogradov symbol times the same q, and that just controls the distance of my rational point from the manifold. Right? So if I have a reasonably good, reasonably sharp upper bound on the number of points lying in this set, then it's pretty straightforward argument to prove the upper bound on the dimension. If you want a lower bound, just the count is not enough. You need to know that they are evenly spread across this region. But in any case, you might want to know something, at least the count. So my problem 2 is under what conditions on tau and f do I have, and what I'm asking about is really what I get when I using the volume argument get the heuristic, and that's going to be so that's the total number of rational points in the d-dimensional cube with this height restriction. Well, once I place these conditions, I have to take away m tau. Okay, so let me give it this name H for heuristic. And again, we're interested in upper and lower bound. Right, so what do we know? I'll really briefly tell you what we know, because I want to save some time for explanation of techniques and results. So basically in dimension 2, we know everything about both problems. So D and H hold for tau between half and a 1, and a 1 is the best you can get. If you ask that f is 3 times continuously differentiable and f double dashed is non-zero, and that's for all x. So these are results obtained between 1994 and 2007 by several people, including Huxley, Dickinson, Vaughan, Villani, myself, and a few further papers where this condition was relaxed in some way, and the bound turned into asymptotic. So high dimensions is really where we struggle up to these days, especially the upper bound. So the only reasonable case when we know more or less everything is hypersurfaces. This is one, m equals 1, so the codimension of my manifold is 1. So there exists an analog, I won't state it explicitly, of the case n equals 2. And this is pretty recent. So the lower bounds are due to I'll come to that, okay? So I just don't want to rush. But the upper bound is a very recent result. So the upper bound was proved by Juan, and the paper is still in the form of preprint. So until quite recently, the level bounds, so this is just refers to the level bounds in those two problems in D and H, existed for tau between 1 over n and 1 over m, and in the case when f is analytic and there is this condition which requires some sort of non-degeneracy. So these functions, one, the variables and the functions themselves are linearly independent over R. So the question which I and a team of other people were looking into is to what extent the analyticity shard assumption is necessary in this context, and basically what else we can prove regarding problems 1 and 2. So let me state the theorem that I'm going to explain. That's one of the two theorems by myself, one and two people in this room. So beyond the class of analytic functions, we've been able to deal with functions of one variable, one real variable. That's why I'm putting this assumption, d equals 1. So my map f becomes f1, fn minus 1. And the condition we impose is that it's Cn, and the Wronskian, so this is just the determinant of a special form of f1 dash to f n minus 1 dash. So the determinant is just formed by this row and then double dash and so on until you get a square matrix. Is non-zero for all x. Then my dimension equation, but in this case I'm just talking about the lower bound and heuristic for the number of rational points. Again, just the lower bound hold for any tau between 1 over n and 3 over 2n minus 1 and sufficiently large Q. Right, so let me just briefly explain the approach. How do you go about showing, for example, constructing irrational points near the manifold parameterized by these functions? The idea is quite simple. You use linearization. So let me draw a picture. So suppose you pick a point on the curve, and suppose you want to find a rational point somewhere in the unicity of this point. It's quite natural, to me at least, to replace the curve with the line. If you're working in high dimensions, you replace the manifold with a tangent plane. Right? So we are seeking for a rational point, roughly in this neighborhood. So if I want to end up with a rational point lying there, I replace the neighborhood of the curve with the neighborhood of the line, and I have to be careful not to make the neighborhood too long so it deviates from the curve. Okay? So you basically take some strip inside and cut it off somewhere. So that's the box where we're seeking for the rational point in, and it's natural, right? It's parameterized by a system of linear inequalities, and as long as we have linear inequalities, we can apply Minkowski theorem for convex bodies to find an integer and eventually rational point in there. So what the system is like? I need to define auxiliary functions. So G, J, just Fj minus this correction factor. And my system is defined by the following matrix: G1, Gm, df1, dx1, df1, dxm, dfm over dx1, dfm over, sorry, should be d, dxd. So it's just the gradient of f, then x1, x d1, and I plug in a minus unit matrix here, and same here. So the minus is not very important, but yeah. Thank you very much. Yeah. Right, so you can check yourself at home that this vector parameterizes, these vectors parameterize the tangent plane. And so basically, when I multiply these by something like that, if this was equal 0, right? So the first M equation just parameterize the tangent plane, and these D equations would represent some kind of line passing here, right? But we don't want a 0. We want something smallish. So to accomplish this, I'm basically taking this system of linear forms, take their absolute values, and ask them to be smaller than some parameters, which I just call psi, delta, and q. So I've got m copies of psi, d copies of delta, and 1 copy of q. right? And to make sure I have a non-zero integer solution, Q, P1, Pn, I have to ask that this product equals 1, maybe bigger, but it would be unwise to make it bigger. So eventually psi will become q to the minus 2, or possibly some constant times that, and this will ensure that my point lies sufficiently close to the manifold. Q will be the same Q as we had before, that controls the denominator of the rational point, and delta is just calculated from here, from the equation. Right, so if I look at these inequalities, so it's basically when I multiply through, it's going to be qx1 minus p1, and it will be in absolute value less than delta. And this is going to be true for each I. When I divide through by little q, this is what I have. When I look at the first m inequalities that arise from this system, just by using the mean value theorem, I can turn them into these inequalities. Let me read them. Say it again?
In the upper line, in the top line, in the blackboard, the top line, the function of GJ. The derivative should be with respect to xi.
Oh yes, thank you very much. You know well it. You've written it. Right. So this is just by expanding this using up to the second term of Taylor expansion. You estimate part of it by psi over q from one of these inequalities, and this is just the error term, the quadratic term. So I also have this condition, well, a priori, I don't know if this is not even zero, but let's assume for the moment it's non-zero, and by swapping the sign, I can assume that it's at least 1. So that means I have a huge range in here, and if q is as little as 1, my rational point that controls the distance of my rational point from the manifold is going to be, well, not that close to the manifold as I would wish. Because here I would divide by 1. So the best result that I can get from here comes about when little q is of the size of capital Q, in which case I divide by up to a constant, the maximal possible value. And this is essentially the key part of the work. To ensure that for a set of x of positive measure, you actually have this condition. So the key step of the proof is to show that, okay, to be more precise, there exists a constant c bigger than 0, such that for any interval I inside 0, 1, there is a subset, let's call it G inside I, of large measure. By large, I mean just constant times the measure of the interval, and for simplicity, I'll just take my constant to be a half. And I have the following condition. For any x in this set, the Q is at least this constant C times Q, where PQ is my solution to the system. Okay, I think it's probably a good point to stop.
Any questions?
So these results are all positive results, right? So they tell us under which conditions we know that these, well, let's say equations hold. Do we have some interesting negative conditions? As in, so clearly, I guess, if we have some form of like degenerate F bar, then we can't have it. But
that's the. Thank you for the question. I meant to save a couple of minutes to say about this, actually. I was a bit slow. So if you don't have, if you can't prove something like this, for example, if your manifold is degenerate, you might be unable to do it. You still have some positive result regarding lower bounds, but not for the rational points. You can still prove the lower bound in terms of equation D. And that's another work, recent, appeared just last year. So the way it goes is it uses basically the same idea for constructing rational points, but once you are unable to verify what you have about the size of Q, we'll be able somehow use what's called Mass Transference Principle to deduce the lower bound. It avoids any count on the number of rational points, but it still produces a positive result about dimension. Regarding rational points, I don't know. It's a good problem.
Further question? So if this is not the case, we thank the speaker again.